All right, our next speaker is Yi Young from Inspur. He's going to talk to us about using OVS to implement a high-performance NAT gateway in a public cloud data center.
Okay, my name is Yi Yang. I come from Inspur. This topic I will talk about NAT gateway in data center. Here, let me introduce our background. In Inspur, we use firewalls from different vendors to implement NAT, including one-to-one NAT, SNAT, DNAT, and traffic control and traffic statistics. But our cloud management platform has to adapt to every firewall. So this effort is very time consuming. It's very valueless and endless. Before, why we didn't do this by ourselves? Because we have some concerns about performance, stability, reliability, scalability, and HA, etc. Currently, no existing open source project can do this. But actually, OVS can do this, right? Linux system itself also can do this. Just we need to do some development work. Here, why we choose OVS to do this? Because OVS is more flexible and more scalable. We only use OpenFlow to do everything. Linux system also can do these things, but we need to use different component. For NAT, we need to use IP tables. For traffic control, we need to use TC. To be important, OS DBDK implemented connection track in user space. So if we have higher internet bandwidth in the future, we can use OS DBDK to maximize NAT performance. In addition, we use meter anchoring to do QoS because this is much simpler than TC QDisk and TC filter. Here is our NAT gateway deployment topology. Here we use bare metal server to do NAT gateway. Here you can see we have two NAT gateway nodes. One is the master, another is the slave. They are connected to core switches. Actually, every NAT gateway node has two interfaces to connect to core switches. One is the ingress interface, another is the egress interface. Every interface can be baud. We use baud to do hardware failover. Here, if a VM accesses internet in compute node, OpenStack neutron will translate VM IP to floating IP, then send the packet to core switch, then send to NAT gateway. NAT gateway will translate floating IP to EIP, then send it to firewall and external routers. For internet client access VM web service, the process is similar, just reverse the path. Here we also can deploy NAT gateway in VMs because In our customers, they have fewer computer nodes, so we just share limited hardware resources. Here we can deploy two NAT gateway nodes into two VMs. Every VM run different computer node. Here the process is similar. Here VM gateway just uses provider network, not a tenant network. In our NAT gateway, we have implemented these features. We can support one-to-one NAT, N-to-one SNAT, N-to-one DNAT. We can support QoS for EIP. Here EIP is a public IP, it's a elastic IP. We also can support shared QoS for multiple EIP. We can support HA. It runs in master-slave mode. We also can support hairpin traffic. Hairpin traffic means EIP to EIP traffic. For that traffic, NAT gateway can handle this. We provide unified command line interface for all these features. Here, let me explain hairpin traffic issue. Here, if we VM1 access VM2 by EIP2, the packet will go to NAT gateway. NAT gateway will translate VM1 IP, it's VM IP1, to EIP1. Then send the packet to a firewall and external router. When the packet arrives and this external router, it will check this packet. You can see for this packet, source IP is EIP1, destination IP is EIP2, right? They are in the same subnet. So this external router cannot handle this situation because actually this break routing convention. So the result is EIP2 is unreachable. So here is the solution we implemented in NAT gateway. In stage 1, source IP of the packet is VM IP1, and the destination IP is EIP2. In stage 2, Openstack neutral will translate VM IP1 to FIP1. In stage 3, NAT gateway will translate FIP1 to EIP1. In stage 4, NAT gateway will translate EIP2 to FIP2. Then NAT gateway will send the packet to the original ingress interface. So computer 2 node will receive this packet. Then Openstack neutral will translate floating IP2 to VM IP2. So finally, VM2 will receive this packet. The final packet is source IP is EIP1, destination IP is VM IP2. Here, let's demonstrate hairpin traffic solution. Here you can see EIP test 001 and EIP test 002. They are VM1 and VM2. Here, it has VM IP and floating IP. Here we log into NAT gateway master. You can see NAT configuration and SNAT, DNAT, QS, SQS configuration here. Here we SH to EIP1. It's a VM1. You can see host name is EIP test 001. Here we pin EIP2. You can see it cannot work because this EIP2 is DNAT. It doesn't work. Here we pin EIP1. It's work. But this is NAT. 1-to-1 NAT. Here we SH to EIP2. It can work. Here we check TCP connection information. You can see source IP is EIP1. Destination IP is VM IP2. Here we SH to EIP1 from VM1. You can see it also can work. Let's check TCP connection information. Here you can see established connection. Source IP is EIP1. Destination IP is VM1 IP1. That's a hairpin traffic solution demo. Here is our CLI. This CLI can end and delete NAT configuration, can end and delete SNAT configuration, can end and delete and update QS configuration, can end, delete, update SQS. It also can do traffic statistics for EIP and for shared QS. It also can monitor traffic. It also can end DNAT and delete DNAT. Here is a demonstration for NAT gateway function. Here we still use VM1. We just pin external machine. You can see it cannot work. Why? Because here NAT gateway doesn't have any configuration for NAT. This is a NAT gateway slave. You can see configuration is the same as NAT gateway master. Here we check VIP because this is a cluster work as a must and slave mode. Slave doesn't have VIP. Here NAT gateway master has VIP. It's 254. Here we end NAT configuration for VM1. We need to use floating IP and VIP. Here we also need to add QoS configuration for this EIP. Then you can see NAT configuration and QoS configuration here. Here we check NAT gateway slave. You also can see the same configuration here. Here we just repin this external machine. You can see it works. Here we run TCP dump to capture the traffic. Here you can see SMP echo request and reply. Here we run iPerf 3 server in external machine to get performance number. We log into VM1 by EIP1 to run iPerf client. Here you can see bandwidth is not good because this environment is our office network. We cannot control other traffic. Actually, in my lab environment, we can achieve about 9 Gbps. Here we can update QoS to set low rate limit for EIP1. I will just set limit rate to 5 Mbps. Here you can see for QS configuration, the rate is scheduled. Run iPop client to get new performance data. Here you can see bandwidth is about 5 Mbps. So that QS does work. Here, if you check average bandwidth, it's about 5. Actually, we also have some challenges to fix. Actually, we cannot implement one-to-one SNAT because our EIPs are from 3 telecom carriers. For every tenant, they cannot get consecutive EIPs, so we cannot use the IP range to do. We cannot support active mode because we cannot synchronize connection track state table between different NAT gateway nodes. We also cannot do load balancing for NAT gateways in active mode, especially for horizontal scalability. That means we cannot support multiple NAT gateways. We only support 2 NAT gateways in master and slave mode. So we cannot distribute the traffic into different NAT gateways evenly. If a NAT gateway node is filled, current existing connections in this NAT gateway node cannot be migrated to another NAT node.
All right, we have time for one question. Who has a question? I think everybody's a little tired and sleepy this afternoon. All right, well, let's thank our speaker one more time.